Hello, do you have trouble determining sample size? Has a lack of knowledge of calculating sample size ever hindered you from doing your research? No problem. You don't need to beg for calculating. If you complete and practice it, you will be a well-versed expert in calculating sample size. This video by the epidemiologist group will make you aware of and skillful in the assumptions needed for sample size determination. The video is essential for determining a thesis or dissertation sample size. The course is necessary for young researchers and those new to research who may have a problem manipulating statistics. It will also give the researcher a basis for precision and power calculation. It is entitled Sample Size for Operational Research, Part 2, Sample Size for Comparative Studies. It will enable young researchers to work on assumptions, power, and sample size calculations manually and with basic software. Before we continue, be sure to subscribe to our channel and ring the bell to get notified about our latest video. On this slide, we want to announce the course's learning objectives. After completing this session, you will be able to determine sample size in two populations for analytic study design. You will be able to explain and describe assumptions considered in analytic study designs and understand precision, power, and maximum variability in sample size calculations for comparative designs. After completing this session, you will calculate the sample size for comparative analytic study designs using EP-Info or OpenEP software. What is new for the sample size of analytic studies? Here, the issue of power and confidence level is important. Therefore, we will discuss those issues. We will also emphasize sample size determination for the proportion in two populations. In this scenario, the sample size for comparative designs, including analytic cross-sectional, case control, cohort, and experimental designs, will be considered. If this is your first time watching this video, please click the subscribe button. Click the like button if you like it. What is behind the designs in sample size determination? The sample size is dependent on the type of design. It is because the procedure of collecting facts differs by design. It is also due to the type of analysis. Therefore, they use two different forms. For example, descriptive designs describe the proportion of events from one group, while analytics assess proportions from two comparing groups. Similarly, case control and cohort are different in the procedure of data collection. Case control starts with the outcome, and cohorts usually start by exposure status. Furthermore, cross-sectional designs start by collecting exposure and outcome simultaneously, with more interest in knowing the outcome. It also depends on the type of major variable used, categorical versus continuous variable. The other issue is based on the power and confidence level required to show a true real difference. Why is there a sample size and power? Sample size and power are essential for evaluating the role of chance. If a study had an inadequate sample size, its results could not show us a real difference. That is, if there is inadequate power in the presence of an association, it will tell us that there is an absence of an association. Because of inadequate power, a true association will be difficult or impossible to distinguish from a non-true association. Adequate power is important for determining an adequate sample size to show a real association. We hear from statisticians about alpha and confidence levels. What does it mean? Alpha, the significance level of a test, is the probability of rejecting the null hypothesis when it is true, or the probability of making a type I error. It is the proportion that mentions correctness, while it is not correct. It is the proportion found by chance. Alpha is usually chosen when the proportion of findings due to chance is less than 5%. On the contrary, the confidence level or limit is the probability that an estimate of a population parameter is within certain specified limits of the true value. It is when a single estimate is inferred to a population parameter. It is based on the proportion of precision, or margin of error. The confidence limit becomes narrow when the precision is very strong, a lower margin of error, due to the high sample size. It is commonly denoted by 1 minus alpha and is expressed with a 95% confidence limit. When alpha increases above 5%, the role of chance is considered high. The alpha value is denoted by the p-value, probability value. If the p-value is high, the likelihood of getting a true difference is minimized, making it difficult to reject the null hypothesis. The p-value set by convention in medical research is 0.05. Therefore, the null hypothesis will be rejected when the p-value is less than 0.05. What is the role of power and beta in sample size determination? Power is the probability of correctly rejecting the null hypothesis when false. Usually, a null hypothesis is rejected when the alternative hypothesis is better or truer, and will not be rejected if the alternative hypothesis is not true. It is commonly denoted by 1 minus beta. On the contrary, the beta is the probability of failing to reject the null hypothesis when it is false, or it is the probability of making a type 2 error. Let us look at this table. Before we go to the table, what is a null and alternative reality? The human brain usually grows, and we hear humans were like animals, then the Stone Age, and later the Mechanical Age, which is known as electronics and digital life. In passing from one era to the other, it is through rejecting the old hypothesis and replacing it with the new, and it will continue. Therefore, the null hypothesis is the current knowledge, belief, and actions related to the relationship between the two conditions. The alternative hypothesis is a new idea innovated, observed, etc. that would be tested in the research. If the new idea is better, the null hypothesis will be rejected and replaced by the new innovative idea. In the column, there is an absolute reality beyond the human mind. In the raw, the table is a perceived judgment, usually by data analysis. There will be no problem when the absolute reality and the perceived judgment are the same, as in the scenario where the null hypothesis is true and the judgment is true, so we do not reject the null hypothesis, and in a scenario where the alternative hypothesis is true, the null hypothesis is rejected. The problem comes when the opposite is perceived. That is, it will be challenging when reality and perceived judgment differ, as in types 1 and 2 errors. Type 1 error is an error that arises when the hypothesis is still true. Perceived judgment judges that it should be rejected, and it is the proportion of reality by chance, also called the alpha, equivalent to the p-value. The second error, the type 2 error, is an error that comes when the reality is that the alternative hypothesis is true. Still, the null hypothesis is not rejected, which is the value of the beta, which is equivalent to random error, also called sampling error. What is rejected, and what does it mean to reject the null hypothesis? As discussed in the previous slide, the null hypothesis is the statement considered a reality current knowledge. If it is tested and found to be correct, it will not be rejected. However, the null hypothesis will be rejected if it is tested and the new science, alternative hypothesis, is better. We should also know that the null hypothesis is the one that will be rejected or not rejected. However, both the null and alternative hypotheses will not be accepted or not accepted. Remember also that the alternative hypothesis will not be accepted or rejected. Before we continue, be sure to subscribe to our channel and ring the bell to get notified about our latest video. What is the relationship between power and sample size? Power is the proportion of an ability to show the real difference. It is equal to 1 minus beta. The amount of beta is equivalent to a type 2 error, which makes it difficult to reject the null hypothesis, while it is wrong, as a random error. At the same time, the power is the proportion of those rejecting the hypothesis, while the null hypothesis is wrong. As we increase the power, we decrease the proportion of beta, the sampling error. Thus, power is directly related to sample size. When we increase the sample size, we can reduce the sampling, beta, error, increasing the power. Therefore, as the sample size increases, the power also increases, as it is in this figure. However, after the power reaches 80%, the increment in sample size will result in a very minute increment in power. Increasing the sample size after getting the 80% power is seen to inflate the cost without gaining much power. Therefore, The scientific community has decided on 80% of power as the minimum conventional mark for sample size determination. As a marker of power, calculating the power may be important after any analysis if no association is found. If the power is calculated and above 80%, we must believe that there is no association. However, suppose the computing power is below 80%. In that case, the absence of association is due to a lack of power, and it may not be a reality, so that others could repeat a similar study. Is there a relationship between alpha, beta, and power? Of course, yes. As beta decreases, there is an increment in power, which is an indirect relationship. The alpha is also indirectly related to the confidence level. As the confidence level goes to 99%, the degree of chance will be very minute. However, alpha and beta are independent of each other. What should we know about sample size for comparative designs? This video emphasizes sample size determination for proportion in two populations. Comparative designs are study designs that could assess the relationship between two groups. You may assess the occurrence of an outcome by comparing exposed and non-exposed groups. On the contrary, you may assess the occurrence of exposure between cases and controls, as in case control design. The following designs, cohort, interventional trials, and cross-sectional analytic designs, are examples of comparative designs. We know the sample size for comparative designs, but what are the assumptions? The following 5 conditions may be important assumptions we should consider in sample size determination of proportion in two populations. The first 3 are necessary assumptions, whereas the others are conventional. The first is to determine the desired values for the probabilities of alpha and beta. We should also consider the proportion of the estimate as variability in descriptive designs, as it is found in a literature review of the same study. The estimate could be the proportion of the exposure for case control or the proportion of the outcome other designs. The third key assumption is an estimation of the expected effect size estimated from knowledge of the subject matter, requesting experts in the subject, and considering the feasibility. The next 2 are used conventionally to compensate for the feasibility. Consider confounder and clustering. Here the ratio between comparative groups and other considerations like non-response, loss to follow-up, clustering, avoiding confounding effect, and inflating the multivariable effect are important. When assessing one by one, the first is the desired values for the probabilities of alpha and beta. What do we need to know? Here, the alpha is the proportion of reality due to chance. The alpha is usually tolerated at less than 0.05, and the confidence level achieved will be z-value at 1 minus alpha is 95%, and its 95% confidence level is 1.96. The proportion of chance tolerated in medical science is about 5%. On the other hand, the beta error is the error due to random error. The random error is inversely related to the sample size. The beta error is usually tolerated at less than 0.20, and it is equivalent to the power achieved at a z-value of 1 minus beta, which is greater or equal to 80%. The value of z at 1 minus beta, or 80% power, is 0.842. The second assumption is the proportion of the estimate. How could we estimate and find it? The second assumption is the exposure estimation for case control and the proportion of the outcome other designs, including the analytic cross-sectional, the cohort, and the interventional studies. If this is your first video, please click the subscribe button. Click the like button if you like it. What and how could we estimate the exposure? Estimation of the exposure is usually done for case control study design. A case control design is also done for rare diseases. In the beginning of study subject selection, we knew how many were cases and how many were controls. Later, in the analysis, we compare how many of the cases and controls are exposed. Therefore, in sample size determination, we usually go for estimating the proportion of exposure. Here, we usually estimate the proportion of exposure among disease-free populations, controls. It is usually challenging to find a disease-free population in the real world. For case control designs for rare diseases, the general public may be considered relatively free of the disease. Usually, the general public is considered non-diseased. Since the disease is considered a rare disease from the literature, the proportion of the exposure in a disease-free population is taken. It is often based on previous studies or reports. It will be a very good estimation if the proportion of exposure among disease-free populations from controls is found. However, since it is done in rare cases, the controls are slightly similar to the general population, so the occurrence of exposure from controls is possible. What and how could we estimate the outcome? Estimation of the outcome is usually made for non-case control comparative study designs. The sample size calculation is based on classical prospective cohort and interventional designs for rare exposures. It is usually for non-case control study designs, including analytic cross-sectional, cohort, and interventional studies. In sample size determination, we know how many are exposed and how many are non-exposed. During the analysis, we compare how many of the exposed and non-exposed have the incident outcome getting cured for interventional. Therefore, in sample size determination, we usually go by estimating the proportion of the outcome. Here, we usually estimate the incidence of the outcome among non-exposed people without the intervention. In the real world, it is usually difficult to find the incidence in a non-exposed population. Classical cohort design, which is done for rare exposures, may be considered relatively free of the exposure. Usually, for rare conditions, the general public is considered non-exposed. For cross-sectional comparative, analytic, design, we don't know the exposed nor the disease condition. We are only interested in the total sample population. We are also interested in the prevalence of the outcome among exposed and non-exposed individuals. Based on this interest, we usually follow the assumptions behind the classical prospective designs. Therefore, we take the proportion of the outcome in people free of the exposure or in the general population from literature. It is often based on previous studies or reports from literature. If the occurrence among the non-exposed population from the cohort study is found, it would be a very good estimation. In the absence of the occurrence of disease among the non-exposed population, estimation from the general population could be used. The third assumption is that we know the expected effect size. How could we know it? Here, it is based on the magnitude of the expected effect size. It is similar to the precision in a descriptive survey. The effect size is more of an estimation than from literature. It is often based on previous studies or experience, that is, understanding the subject matter well. It is based on the clinical or public implications of the difference. A minimum effect that the investigator considers worth detecting is usually selected. The expected effect size could be measured based on the absolute or relative difference between the index group's cases and controls, or exposed and non-exposed. The two options are A, the relative difference, which uses the relative ratio for prospective designs, and the odds ratio for case control and cross-sectional designs. And B, the estimated change is based on the absolute difference in your exposure that would change in magnitude. Both options are asked in sample size determination using software, and you have to choose only one of the two. Estimation using a relative difference. The odds ratio, or relative risk, measures the relative difference. The relative risk for cohort or interventional studies is the odds ratio for cross-sectional or case control. The assumption of estimating the odds ratio, or relative risk, should be based on the clinical or public implications of the relationship. If there is no knowledge of the clinical implications or interest with high eagerness, it is better to estimate using a very minute difference. You may base it on scientific merit, cost, and feasibility of the research. When the cost or feasibility of doing the research is difficult, you may want to consider a wider difference. But such selection is based on a risk that the sample size may not be enough. In such a condition, if you find no association, you may calculate the power, and if it is below 80%, you should consider it a lack of power. It would help if you chose a small odds ratio or relative risk nearer to unity to depict a slight difference. As self-estimation to find the minimum desired difference, you start from a minute difference and continue step-by-step increment. Example, you may begin with an odds ratio of 1.25, then 1.50, and continue to 1.75, 2.00, 2.25, 2.50, 3.00, etc. It would be best to stop calculating when the number is feasible for your research and consider taking a risk. For example, suppose you chose an odds ratio of 1.5. In that case, it means that if the actual difference has a real odds ratio above 1.5, using this calculated sample, you can observe a difference if there is a real difference. However, if the difference has a real odds ratio below 1.5, the study's calculated sample size is insufficient. The other estimate of the effect size is using an absolute difference. The absolute difference is the other alternative used to estimate the sample size. The absolute difference is the expected difference between the estimates. By subtracting the difference between the proportion of those exposed to disease-free and an estimated proportion, one can estimate the sample size. The minute the absolute difference you choose, the higher the sample size will, to provide high power. When determining using software, both absolute and relative differences may come into play. You have to use either the absolute or relative difference. Sometimes, you may consider the absolute or relative difference from similar research. In such a scenario, you have to accept a slightly lower effect size, otherwise, you may be at risk. 4. Ratio between cases and controls. The ratio between the two groups in analytic studies should be considered. Case control, cases versus controls, cohort, exposed versus non-exposed, interventional, intervention versus non-intervention. A ratio between control and cases is considered in sample size determination, case control study. A ratio between non-exposed and exposed individuals is considered in a cohort study. In an R/1 control to case ratio, how large should be R? Since finding cases is difficult, a higher ratio of controls to cases could be made. Defining the ratio is based on the gain in power in terms of precision. The justification is based on the Pittman efficiency criterion. There is little increase in precision by using a ratio larger than 4. As the ratio increases to 4, 5, 6, etc., the power received will not be much, but the cost of collecting from such a huge number of controls will be inflated. Therefore, the ratio of controls to cases could range between 1:1 to 4:1. Other considerations. Here, we may consider a non-response due to refusal, absence, non-existence, not reaching, incompleteness, especially for self-administered data collection, or loss to follow-up, cohort experimental studies. In such conditions, adding 10 to 15% of the sample for each group, cases and controls, is important to adjust the power. Moreover, while exploring risk factors to suppress confounders, 10–15% of the sample should be added to suppress major possible confounders. How should we write the size of study subjects in a proposal? The sample size of study subjects in a study should be based on the type of design. For cohort or interventional designs, the size of study subjects should be described by their exposure status or intervention status, whereas for case control designs, the sample size of study subjects should be described by their caseness or control status. Therefore, during the proposal and later in the manuscript, the sample size should be stated by describing the size for each group. You should show how many are cases and how many are controls, but you should not sum up the cases and controls and write totals. However, for cross-sectional studies, you should describe the total number of study subjects as a single group. If this is your first time watching this video, please click the subscribe button. Click the like button if you like it. What assumptions are made in a proposal? We should describe the sample size determination method. That is to describe whether you used sample size determination for proportion in a single population or sample size in proportion in two populations. Describe the variability, that is, the outcome or exposure to diseases free or exposure free, respectively, from the general population. Such facts are usually taken from the literature, so providing a reference is important. Describe the size of the effect by taking the minimal absolute or relative difference warranted. This effect size is usually taken from experience. It is more estimated through considering the possible minimal estimate. Consider two things: the confidence level, usually 95%, and the power estimate at 80% or more. Consider also calculating the ratio between controls and cases, or exposed and non-exposed. Finally, write for some considerations. It may be necessary to compensate for problems such as non-response, loss to follow-up, missing data, confounding, issue of cluster sample use, etc. The formula for proportion of two populations. This formula is a general formula for comparative designs, where n is the sample size in the case group to represent one of the groups. R is the ratio of controls to cases, or non-exposure to exposure. At the same time, the P represents the average proportion. It is a measure of variability, similar to standard deviation, P1 minus P2, to show the effect size, the difference in proportion between the two groups. The z-value of beta and 1 minus alpha also show the confidence level and the power, respectively. Although sample sizes are done using computer software, knowing what the computer does may be important to some of us interested in doing it manually. Many software can do sample size, but the EP-Info and the EP-Open are accustomed to in many medical and health colleges. The procedure using EP-Info is as follows. First, we click the icon for EP-Info, and a window dialog opens. The window contains create forms, enter data, create maps, stat-calc, and the classic and visual dashboard. Here, the stat-calc is important for sample size determination. The stat-calc is used for statistical calculators for sample size, power, and tables. By clicking on the stat-calc, we can find the different functions of the population survey for descriptive designs. The cohort or cross-sectional for comparative designs using the outcome as an estimate, and unmatched case control for comparative designs using exposure as an estimate are parts used for sample size determination. The first thing, here, is unmatched case control. When we click the unmatched case control, we find points we have to put in. First, we must adjust the confidence level to 95%, the power to 80%, the ratio between control and cases, and the proportion of exposure among people free of the disease. Then we have one option to add, the effect size, either the minimal proportion of the exposure among cases, or the minimal odds ratio to show a minute difference. Finally, we can see the sample size for cases and controls based on the two authors Fleiss and Kelsey, and the corrected Fleiss.